Good afternoon, sir. You can go ahead with your presentation.
Yes, basically, it is coming from how the high voltage is required, why the high voltage is required, then why we have to go with the GIS, then what are the components of gas insulated switchgear, then what kind of testings are available, what are the technology involved in the manufacturing of the individual components of the gas insulated switchgear, then the condition monitoring of the switchgear. This is our basic program. Here in this first slide, if you see, this is the one of the 145 kV GIS. Some of the components which we are currently manufacturing is in the left hand side. These are some of the components. So when you go with the high voltage, why we have to go ahead high voltage? These are known to everybody because of the various voltage drop and the system stability, right of way requirements of the high voltage. We have to go with the, these are the critical requirements for the high voltage lines. Then if you want to increase the power transmission from means power transmission for the highest energy, you may have to increase the voltage. So if you see the reference at when the voltage is increasing 400 kV to 1200 kV, the power is almost increasing by 10 times. So this is the requirement why we have to increase the voltage. So this is the double circuit line. When you increase the voltage from 800 to 1500, how much power is being transmitted over the line? Then that at the same time, the height of this tower is 800 kV, it is about 91 meter, and for 1200 kV, it is 123 meter height. With this, it is possible to make the transfer of the more than 10 gigawatt energy with a double circuit. So this is a reference for the high voltage line, how this is constructed. This is a double circuit 1100 kV line. It's about 110 meter height. So these are the components of air insulated switchgear. Before going to the GIS, we have to understand the need of a gas insulated switchgear. These are the components. If you see any high voltage substation, you have the big structure, the high about even up to 40 meter height. Then the length is, if you see for the 245 kV line, it's about 178 meter length. This is a complete substation length. It is coming like that. So how? Because the air insulated switchgear is exposed to the atmosphere, because of that, it takes a lot of problems related to the environmental issues will affect the performance of the equipment. This causes the reliability issues in the every equipment of the substation. So these are the components involved in any of the substation equipment. Before going to the GIS, to understand the components in the air insulated switchgear, it needs the measurement of current and voltage, generation of the transfer of power from one voltage to another voltage, and disconnectors, circuit breakers to switch. All those are the part of the components in the substation T&D line. So to understand the clearances for the various voltage ratings, for 66 kV, the face-to-face clearance is about 2 meter, and hence the right of way, the total length is required is about 18 meter, and the 132 kV face-to-face distance is about 2.7 meter. These numbers are to have a feel of why the GIS is required to have a smallest dimension. That's why the numbers are shared with you. When with 132 kV, it's about 22 meter, and 220 kV, it's about 35 meter width is required for one way, and for 400, it's about 46 meter. Clearance between the face-to-face is about 7 meter. So there are substations are divided into three types, basically depending upon the construction of the substation. In this air insulated switchgear, where you have the main bus is in the air, and the gas insulated switchgear, the main bus is in the SFC's gas. So these three, conventional air insulated switchgear and hybrid is a combination of the both. This is air insulated switchgear and GIS. It's between that it is hybrid GIS, or they call mixed technology switch substation or switchgear we can consider. So in the conventional AIS, the equipments are distributed. It's not in the it is in the one, not in the one place. It is distributed with the required statutory clearances. And the hybrid is combination of both, and it is highly integrated within a small space. So the live pods are exposed in a conventional AIS, and is fully enclosed. It is combination of both again. The overall land area is very high for the conventional AIS, and for the GIS it's more relatively. You can see how very small it is. So if you see the air insulated switchgear, you have all exposed, the all circuit breaker, disconnector, air switch, even the transformer, everything is exposed to atmosphere. So it is highly influenced by the atmospheric conditions, sun, solar, chemical, sand, and the wind, and then the chemical. All those are influencing, and it is not very good. The reliability is hampered. So if I have to compare these three technologies, GIS, hybrid, insulated switchgear, AIS, reliability point of view, GIS is most reliable. As I said, it is confined to the small area, and it is fully controlled because the individual equipments are completely enclosed, and it is pre-tested. It's tested in the factory. It is assembled in the site as a complete bay. So the chance of having error other than the transportation is nil. So in that case, the reliability of the individual component is increasing. So the total switchgear reliability is very good. The maintenance and operation point of view, compared to the AIS, it is slightly difficult because once you want to operate in any one of that, if you want to do any maintenance, you have to have a initial design plan. The maintenance requirement has to be considered during the manufacturing or design of the substation itself. Otherwise, it will be difficult because once you select the single bus bar combination, where you don't have the spaces which will have the separate enclosure, it is difficult to do the operation. So maintenance point of view, we have to design it very properly. So if with that option, the maintenance of this is very easy in the GIS compared to all other switchgears. Installation, because it is completely manufactured in the factory, and it is only the bay wise it has to be assembled in the site. The installation easiest one. Layout is very compact. Then the expansion, it is easier because whenever the design of GIS component is made, it is considered with the expansion requirement in the future. So there are space given for the additional base. So considering that the expansion is very easy, this land requirement is not critical for the expansion. So in that case, it is easier. And the construction cost. The construction cost is very high because the manufacturing of this is very critical in a factory. So the manufacturing of individual component is very controlled atmosphere you have to do. That's the components are very critical. Every part is carefully handled. So considering all those, this equipment cost is too much. That's why the construction cost is highest compared to the things. The hybrid, and it is high, and the air insulated switchgear is the lowest in terms of capital equipment cost. There is a here the presentation has a lot of content which are mostly coming from the SWIGRI documents. So this is the one of the comparison in the one of the document. So where this is more critical, and see when it is plus, it is favorable. This is a neutral one. it is a -1, it is lesser, it is inferior. That is the thing we have to understand. So location point of view, if it is outdoor, the space is unlimited. So you can utilize much better than other. So AAS is suitable. Outdoor and urban requirement, this is more suitable. If you see, then indoor, whenever if you want to make the substation indoor, GIS is because it needs a very small space, height wise also. So you can go with that. If you want to make the underground substation, still GIS is superior. Then if the container, the substation can be made, there are prefabricated, so substations are available. There are IEC is also formed for the fabricated gas switchgear requirements. So for that also, GIS is critical. And that the container substation, what is the interesting is you may have to carry that to the substation where it is already functioning. You have to carry it and transfer the power through this switchgear. For that purpose, you may have to have a mixed technology switchgear also, because this is also suitable for both application. And when it comes to the equipment design and manufacturing point of view, this is a very good one. This the experience is very high, because this has been more than 100 years of technical experience is there. And this is also having about 50 to 60 years of experience. GIS is also is from the 1960s onwards, people started manufacturing this technology. So this is also a good one. But relatively, air insulator switchgear has been in service for more than 100 years. So the design is known to all the people. That's why they given the plus. The material is almost same. Manufacturing process and quality control requirement is highest in the GIS, in the particularly, manufacturing process is very critical in the gas insulated switchgear compared to this one. But IAS, that is not more critical. So it is easier to procure those materials compared to the GIS. So quality requirements, state of the art, this is all. This is a project engineering point of view. Project, this is the individual components is kept in series one by one. So a project is not complicated. It is all material is, but problem is engineering point. It has to be pre-planned very meticulously to have all equipments. But in case of the GIS, all components will come together. So it is easier. Contract schedule can be reduced. That's why GIS is better in terms of planning the substation in a short time. Civil work is not very critical for the GIS, because it has very small area. So civil work is having very less cost. Particularly, the AA substation needs the big gantries, the big steel structures are required to carry the weight and for the seismic requirement and all. But in gas insulator switchgear, it is not that critical. That's why, because the height of the product is not that much like AAS. So the GIS requirement is very, it can go higher seismic requirements. So these are the other these things. Construction is possible in the AAS, but GIS it is not possible. These are some of the advantage and disadvantage. Impact on environment. Here, the most of the cases it is in GIS. GIS is very good if you see this aesthetically, because you can use it in the rural substation, rural areas, and urban areas where you wanted to have very good aesthetics. Also, there also you can use the this in the park area. Also, people can use the GIS. So the noise point of view, because this is enclosed where the people are working inside, that's why it is contained into the box, so it is better. But the sound is common everywhere. In the aerosol switchgear also, circuit breaker sound, the noise is same as indoor one. But here it can be minimized as it is put into the enclosure. So leakage point of view also almost similar. EMI, EMC interference is not there. It's there, but it is very less in GIS compared to the AAS. In fact, off environment is also very good with the usage of GAS is very good because pollution, corrosion, seismic conditions are prone, means it can be used in those conditions, worst condition also. So these are the advantages. Availability is very high, almost one. This is compared to air insulated switchgear, the gas insulated switchgear is almost 1/3 only. So availability is much better than AAS. The lifetime is almost 40 years. It can be extended by replacing the certain aged components. It is easier for the man. In the case of AAS, it is very easy. Suppose one circuit breaker is not in good condition, you can replace circuit breaker. But in the case of GAS, it is very difficult to replace only one component. It's very difficult to replace one component. That way, operation maintenance point of view, that is easier to handle, but this is not difficult. It can be because nowadays, based on the new technologies, condition monitoring and all very easy in the gas insulated here in a LCC, we used to put all the components required for the condition monitoring. We can do that. So now the testing, flexibility, personal safety, physical security, and all those points. This is superior. GAS is superior compared to AS. Now, to have idea about the space requirement for this, the comparison is given. If you see, this is about 10% of the total length for the 132 kV substation. Mixer technology, you have about 60 meter. This is about 20 meter. About 200 meter length is required for the complete substation one way. But GAS, you need only 20 meter length. You can accommodate everything, and the space is very less. So where the land cost is so much, you can use gas insulated switchgear. This is also another example for to understand the severity of this one. Again, this is a 245 kV substation. Here, if you see, this is about 57 meter length. This is changed into only 11 meter length. If you see the diameter of the, if you see the insulator, the height is about 6 meter here in the case of air insulated, but this height is here is about 0.5 meter only. This is a bus bar diameter of this is about 0.5 meter only. This much size you can reduce to have a total cost of these. So based on that, now it has the highest reliability in the smallest space, almost 1/10 of the AS. Virtually, it is maintenance free. It should be a fit and forget product. If you don't have any major problem, in case of it can be monitored in case of any issues. If it is degrading over the many years of usage, it can be measured. It can be some parameters can be checked to see the condition of the switchgear. So that is also possible. So personal safety is very good because there is no chance of explosion related issues. In the case of air insulated switchgear, any component can get damaged, or it can be broken, or it can be blasted, and it can lead to the personal, it is more lethal. AS is more lethal than the GAS. Security against vandalism and terrorism is not there. The modular design, it is some components can be interchangeable because one spare component can be used any of the bay. It has a low weight compared to AS because it's very small space, so it is low weight. Shortest erection time because it's a pre-assembled in the factory. It has the shortest erection time at site. So this also just to have idea again. The size is how much it is. Volume wise, it is just 5%. See, the box if I use is about 40 meter height, as I mentioned earlier. There's a total volume occupied by the GAS is about just 5% only. There is a CBIP comparison also for the cost. The cost point of view, this is GIS. The capital expenditure is very high. Very high means about 20 to 30% higher than the IIS. Otherwise, all other total expenditure, the total life cycle cost is very high, very less for the GIS. Wherever you want to have strategic substation in the network, you can use these GIS components. Wherever the highly polluted areas are there also you can go with that. Whenever you have the mountainous and the heighted areas where you have the hydropower plants, you don't have much space for the areas, then you can use the GIS application. So thermal power plants also, the land acquisition is very difficult to those areas. Mobile substation and underground substation also, we can go with the GIS. These are some of the applications. Now, there are certain configuration commonly used in the GIS gas sensor switchgear. Here, if you see, this is a single bus bar. The single bus bar, one bus bar. There are incoming line, it's outgoing line. So, so this is a double bus bar scheme. Depending upon the reliability of the network, single bus bar scheme can be used on double bus bar scheme. If you want to have more reliable relatively with the critical substation, you can go with the 1.5 circuit breaker scheme also. This is, you have the 3 circuit breaker for the 2 bus. So these are the 3 common, very common schemes for the gas sensor switchgear. This is for the cost comparison. When you compare with the AS and GAS, if you see this one, planning time is nil for this one, and the equipment cost is high for GAS. If you see this, and the controls and this cost is almost same, and the cable cost is very less. Here, if you see, it is reduced, and here the civil work cost is very high. Civil work cost is very high for the AS compared to this. So here, the lot of saving is made with the civil works. The totally, if you see this, this is almost 130. It's about 100. So almost 30% lesser cost compared to the AS. That's the advantage of GIS. See, this is an example for the 6 base of AAS. It's an indoor substation where 6 bay of AS is converted into 5 bay of GIS. It's 150 kV AS to 140 kV GIS. With this, how much space it is occupying? See, this is very small. So total area is now this much space is available to play or anything, whatever. So this is an example for the this is the underground substation. In the any of the floor you can use it. Over that you can put anything, the people can play. So there are some many places where parks are made over the substation. So here also, this is in the shopping complex, 23 base of 145 kV GAS and 4 base of 362 kV GAS and transformer hidden in the shopping complex. The look wise also is very good to use. So this is another substation. These are the few of the samples of three-phase in a single enclosed chamber substation. It's about 145 to 170 kV. People use 3-phase enclosed enclosure. So this is to have idea how over the years it is reduced the space. In 1970s, for the same person, the height is how much it is, you see. And it is so 1980s, it is reduced, and 2000 it is reduced so much. So this is a way how the 245 kV GA substation is reduced in the volume. See, when you come to the components of the GIS, there are majorly 4 components. Mainly the 4 components are used in the gas insulated switchgear. Mainly the conductors, it's our live parts of the device, usually energized to pieces. Then metallic enclosure. Normally it is aluminum. Many people use the steel structure also for the enclosure. Nowadays, people are reducing to use, or they are not. They are restricting to use the steel enclosed switchgear. So this is insulated. This is for the support of this one. So here, this is guiding the live conductors. This is a line. high voltage line is here. This is the insulation, SOS gas. This is the in the pressurized condition. Can be SO6 or nowadays the new gases are coming. So that can be any of the gases. So other than these four parts majorly used in the GIS, the fifth element, this is very important because the cleanliness of this is very important in the GIS, and also it is very critical. If the component is not very clean, it can cause the reduction in the field uniformity is going down, and it can cause the discharges and the particles. If there are particles inside the switchgear, then it can cause the failure. I mean, so it starts hovering and it can create the failure, or it can go into the critical part of the insulation and it can bridge the high voltage line into short circuit, so it can cause the failure of the equipment. So the cleanliness of the equipment is very important. Even for the during the assembly, even smallest dust coming in contact with any of the critical area of the field might definitely create the problem. This is very important. So the cleanliness is foremost important in the JS. Here, if you see again, these are the gaseous components, enclosures. Then the active parts, when you see this is a live line, this is the shield where it is connecting the chamber. See, when you have the spacer, this is called spacer. This spacer is restrict the movement of the gas from one chamber to another chamber. So this is an enclosure, one enclosure. This is so it's a one gas chamber. So the gas is not moving from one to another one. So there should be a gas monitoring device in between. So if you see this very carefully, in the enclosure, this is a critical point. If this is not rightly done, manufactured, this can fail. This can lead to the failure of the equipment. So this is very critical component. This is a spacer. Sometimes it is made into the communicable type, non-communicable, both are there. So one of this is why we have to use the SOS gas. It's known to many of the people. So just I'm going through very quickly. The SOS gas is a greenhouse gas. It is though it has a very good electrical and thermal properties compared to air. It has the highest greenhouse effect relative to other gases. That's the reason why people are going to shift, or they are shifting, or they already shifted. Some of them are shifted to the new gases to have a lesser greenhouse effect gases. For example, people have come up with alternate gases in 2010 onwards. There is a thrust more of a new gas introduction for to replace, because the fluoric gas is not good. The SF6 byproducts are very harmful, but SF6 is very stable. It's not toxic, or it is not reacting with any other. It's a very stable gas, but its byproducts are not good. And when this lifetime of this is about 3,200 years. The stability of this gas is very high. Because of that reason, this greenhouse effect is very high. That is causing almost 2,300 to 400 times worse than carbon dioxide. Even you have the carbon dioxide, this is one, then the greenhouse effect of global warming potential of the SOS gas is about 2,300 to 400. So that's the reason why internationally people are putting more pressure to reduce the consumption of the SOS gas. So that is one of the initiative to reduce the gas volume by reducing the size. So the optimization of the equipment is going on reducing. That is one of the reason. And nowadays people are thinking of going for the new gases. New gases means there are there are few fluorine based nitrofluoric fluoroketone gas are come. People are using in some of the manufacturers are using those gases. The old gases like CO2 and air also being used by many of the manufacturers by saying that it's a more it's blue gas, green gas, like. So there are different manufacturers are coming with new ideas, new methodology, or to marketing ways to say that this is more environmentally friendly gas than SOS gas. So the usage of SOS gas is going to be limited over the years, but still SOS gas is dominating as a major insulating gas in GAS. So because of this structure, this is more stable and it's not flammable. It's chemically stable, symmetrical molecule. If you see the 6 of the fluoride, these are around the sulfur. The fluoride is in the 6 composition are here. So that's why it is more stable. People are finding to better than this gas. SS gas also has some of the liquefaction limitation when it is required to be used in the very low temperature, because circuit breaker where it is kept low temperature less than -40 and all, it is very difficult to use. So it has to be used with the heaters to maintain the temperature more than 30 degrees, -30 degrees any rate, or if the temperature is going -40 or below at a 5 bar pressure, and it can go to the liquefaction temperature, it can lose the property in that case. So the newer gases who are found also, when it is having very good dielectric properties, these are all not good temperature requirement. So that also has a limitation to use in the lower percentage only, because there are a few gases found with a better electrical properties, but it is limited temperature application. That's why it has to be used in a lower concentration, like the 15%, 20%. The remaining will be more of carbon dioxide or nitrogen, like. So people are trying with a different composition. Yeah, it is in the service now. Many utilities have tried to use it in their modern substations. So here, if you see, the SS gas have very high arc quenching property compared to other gases. So this is the reason people are not able to easily change the gas into other gases. There is a Kyoto Protocol in Japan to minimize the usage of gases. So in 1990s, they have done to reduce the gas usage. Based on that, see, if you see this gas levels, parts per trillion volume. It's not parts per million also, not parts per billion also. It's parts per trillion. So but though it is very, very low compared to the carbon dioxide, which is abundantly available in the atmosphere, which is really main cause for the global warming potential, where the temperature is continuously increasing 0.5, 0.2 degree over the years. But though the gas is, the SOC gas application or it is exposure to the atmosphere is contributing merely 0.7% only in the global warming potential, because it has a highest global warming potential of 2,300 times more than CO2. That is the main reason for having this one. But quantity is the PP is parts per trillion volume is very, very low. That is causing about 0.7% of the total global warming potential, or it's almost less than 1%. So it's very less. If you see, the most of the biggest contributor for the global warming potential is about 65% carbon dioxide, because carbon dioxide is due to a lot of emissions in the vehicles and all other usage, like everywhere. So this is the major reason. And CH4 is about 20%. Other gases are about 10%. Gas is not seen anywhere because it is less than 0.7%. That's the reason which is contributing very low for the greenhouse effect. So a few years before, there was no alternate gas. A few years before means, if I want to say, it's about 10-15 years before, there was no real alternate gas. We had to go with the air, because the reason why we came to SOC gas was due to the perfect arc quenching capacity and its high dielectric strength. So people moved. Actually, the technology initial in the circuit breaker was air blast technology. The air blast is like buffer. It is air is pressurized when the breaker is operated, and it extinguishes the arcing. The same now, whether we want to go into that, there are people who are suggesting with that advanced drive mechanism and higher pressure. People are able to meet those requirements now. Yes, there are possibly mostly the medium voltage circuit breakers are using the alternate gases, the clean air or the dry air people are using, but the breaker is still vacuum interrupted technology, and the vacuum interrupted technology is it can be updated up to now. It's about 145 kV commercially available. So up to 145 kV SS gas can be fully replaced with the vacuum circuit breaker technology and any other alternate positive pressure gas. Yeah, we can use depending upon the electric field intensity on the surface of the conductor. We can modify it to improve, and it can be used for the circuit breaker up to 145 kV without any. So we can hugely reduce the usage of SS gas by using the vacuum interrupter technology up to 145 kV. More than that, we have to find the alternate gases. There are available alternate gases. People have claimed that it is fully implemented in up to 300 kV application. Yeah. So these are the bodies, working bodies, who are controlling or giving guidelines for how to use the gas. This is fluorine-based gas. Particularly CAPL. CAPL is the body, and it was basically is a group work for the reduction of the global warming potential gases. So people are working on the SF6 recycling techniques, and eco-based designs are brought, and the inventories, the materials are reduced, and life cycle assessment softwares are available to estimate the life cost of product, and alternate substitutes are also worked out. So all are working to change the gases. So it was the 1990s. This was given. USA has to reduce 7%. Japan has to reduce 6%. Europe has to by 2012, before 2012, and a lot of work is still going on. All these are the greenhouse gases: HFC, perfluorocarbons, nitrogen oxide, methane, carbon dioxide. So some of the alternate gases in the this is a fluoroketone, ketone, and heptafluoropropane. These are the few gases, and fluoronitrile also another gas, which is used for the application of essentially the same application. See, the medium voltage switchgear also, medium voltage gas insulated switchgear nowadays. People have tried to, because it has already, the circuit breaker is used with a vacuum interrupter, and the gas around the circuit breaker and disconnector switch, earth switch, and all can be used with any of the gases with a higher positive pressure. So people have suggested to go with a slightly higher pressure and improving the surface of the conductors more uniform, and it can the space can be reduced, and we can use the same width. Wavelength can be maintained same with a positive pressurized dry air or clean air technology also, instead of SLS gases. So medium voltage switchgear, it can take a faster replacement than higher voltage. For example, 72 above 145 kV. The pace is slower, but it's stable. People are using the gases. So these are the other gases. When you say oxygen is used, nitrogen can be used. Carbon dioxide is also used. Synthetic gas. Synthetic is the purest form of it's 80, 20%, 90% nitrogen, 20% air is used as a replacement. So these are the, and fluoronitrile also used as another one. So if you see the application, this is about 1.3 bar pressure is the pressure of the medium voltage switchgear. This is fluoroketone is the gas, almost 13.6%, and oxygen is 17.3%. Nitrogen is the remaining. It is almost 30. It's about 60, 70% almost. People are using nitrogen. 70% nitrogen is used with the fluoroketone and oxygen. with this one. In the high voltage application, the same gas is used with a higher pressure. Here also the fluorokit is about 4% and 14% of oxygen. The remaining is carbon dioxide, still nitrogen or high carbon dioxide is used to have a better or quenching property than nitrogen. So it is used. So there's another gas, the fluoronitrile C4FN. Here, this is used with a 99.4%, 99.5% can be used. So after this, now we'll come to this aluminum enclosure. So one of the part of this GS is aluminum enclosure. Aluminum alloy enclosure provide following advantage over the steel enclosure because it is corrosion free and you don't need to have additional painting. So, such it is not required, but normally customers ask to have the color on the aluminum enclosures. Maybe different colors are suggested by the people because internally there is no paint as such, but there's people, some manufacturers use the epoxy coating on the surfaces, but still generally it is not used because the loose paint particle could create the flashover. That is one of the reasons why they don't use it. And this is corrosion free material, ensures that SLC sealing will remain perfect during the entire GS life. So low electrical resistance directly reduces the thermal losses. When the resistance is low, ice cold losses in the enclosure is also reduced. So non-magnetic material, this aluminum is non-magnetic material, so no electromagnetic losses from eddy current. So higher return current provides the better electromagnetic shielding. Almost 70 to 80% of the, suppose if the current conductor is carrying about 2000 ampere current, then it can, this enclosure can, because the induction and creates the current, it can cause about 80%, 70 to 80% of the current is passing through the enclosure. This is acting like electromagnetic shielding. So, and aluminum is relatively lower density material. It's about, the density is about 2.7. So compared to the steel is of 7.65, it is almost 1/3 of the weight, and weight to strength to weight is very good with the aluminum. That is the reason why aluminum enclosures are suggested to use everywhere. So it is GIS is kind of Lego blocks. You have to connect different circuit breaker module, then the current transformer module, voltage transformer module, different modules. So these modules are connected to have, it's kind of Lego blocks assembly. So every block is in a way, every block is used as a used for the particular function. For example, if you see it's a switching, circuit breaker is there, measurement, current transformer and voltage transformer, and other monitoring devices used for the connection. Connection is between the one compartment to another compartment, and feeder connections and overhead line connections. Then wherever you are stopping the connection, is disconnection, earthing, extension, surge arrestor. These are all the function, particular different function, different blocks are used, like a Lego block, I said. Yeah, now. So you might have seen there are application of three-phase enclosure and single-phase enclosure. So basically, this three-phase or single-phase, it is based on the cost, where the cost is feasible to apply, people go with that. That is a major advantage. But there are disadvantages also, some of the advantages. So three-phase encapsulation has some of the advantages because of the compactness. It gives the three-phase are enclosed in a one enclosure. Okay, so it's very small, the weight and its height is reduced. It has less connection because if you have three phases, you have to have three separate box for individual phases. So you have to have almost 1/3 of the box, the number of enclosures will be reduced. So in the single phase encapsulation, it has advantage of better flexibility with a complex single line diagram. You can change anything easily. Single phase elements simpler, smaller, and more economical to replace in case of higher voltage ranges. This is 140 kV, how this is connected. This is about, you see, it's a 145 kV. The total height is 2.5 meter, and the length of this bay is about 3.75 meter. The width is about 0.8 meter only. You can see how it's compacted compared to AAS. This is the this is a way how why GIS is widely used in the higher kV ranges also now.
Muthuraj sir, I have one question. This is
Yeah.
Balaji here.
Yeah.
So in the previous slide that you have shown, all the conductors inside the GAS, they are lying in straight line and not in not in the vertices of a triangle, sort of like 120 degrees spatially spaced apart. So why is that so? It is better, no, if we have 120-degree spacing.
No, it is also there. If you see this one, now it's 145 kV. See, in the bus bar section, people use it in the because it is basically the connection, how this is connected. If you see, I'll take a water.
Yes, sir. Tell, sir.
Yeah.
I mean, I think.
He's having water.
Okay.
Oh, all right.
See, this is a 3-phase line. You have R phase, Y phase, or 3 are connected in 120-degree shift here. Here, this is in a straight line, because the connection from this to this is very difficult to make it in the same line. 120 phase shift is not a practical. When the components are manufactured, it is not decided that way. The components are manufactured, the people look for the similar components can be modified to use here. If you see this one, when it is shifted from 120, see this is straight one actually. This is here the straight one, 1 to 3, the phase R, Y, BB, or one behind another one. But here it is twisted when it is changed. Here also it is in straight line. So both way it is possible to make. Some manufacturer can make it in a 120-degree shift also, based on their requirement. Basically, manufacturing easiness, people prefer to go with that. There is nothing like whether we need to have 120 degree or in the same line. Depending upon manufacturing feasibility, they choose the whether it should be in the 120 or it's in straight line.
Okay, sir. Thank you.
But it's all everywhere. Different people uses the different methods. When somebody uses in the transition area, they make it in 120 degrees. Somebody make it in the straight line. So the Korean manufacturers, even they don't use this kind of transition. The 120 degrees, they don't use it. They use in a straight line only here. So here also it comes straight and it goes in a straight way. So it depends on manufacturer, their easiness of manufacturing the components and assembly. They decide to go with which configuration they wanted to go with. So I'll quickly go through this. Actually, the time is not there. So this is a pointer is not working. See, what happened?
Sir, we have exited from full screen mode. Now it's working. You can see the pointer.
Okay. See, this is a circuit breaker, and circuit breaker, this is a double bus bar scheme where you have the 2 buses are there, and the connection is coming from, this is a feeder line. Feeder line is coming through the circuit breaker like that. It is connected to the bus bar like this. See the 3-phase. Now, in between that, there are disconnectors and switches. And here this current transformer can be within the enclosure of the circuit breaker, or it can be a separate enclosure, depending upon customer and the maintenance requirement. They do that. Now this case, it is inside the gas chamber. Many of the supplier, manufacturer put it outside the gas enclosure of circuit breaker. Now this is a combined 3-phase combined disconnector. This high-speed switches here. And then this is a cable socket where the cables are taken. And another view. This is a voltage transformer. This is a extruded view of the components. This is again the circuit breaker. This is spaces. These spaces are acting like it separates the gas movement. So it says enclosed, and the enclosure is supported by the spaces in both sides. So here circuit breaker is enclosed with the three spaces, three spaces, and this divides a gas compartment. Now here the voltage transformer, it also has its own gas. Sorry, this is a spacer, and here there is one more spacer. It can have one spacer or it cannot have. It doesn't require. It's not a mandatory thing. So depending upon the configuration, customer specification, people choose which configuration they wanted to go with, whether with the spacer required or not. They decide depending upon the manufacturing and the requirement of the customer. They select. And the breaker is operated by the drive mechanism. The olden days people were using the hydraulic and pneumatic mechanisms. Now also at a higher kV level, some of the manufacturers are using the hydraulic pneumatic mechanism. Most of the time, most of the manufacturers have come to the spring operated mechanism, and the future it may go into the any other mechanism also, because the spring drive mechanism has so many components. It may have so motor directly, DC motor can also, servo motor, whatever. There are different mechanisms will come in the future. This is the maybe with this 420 kV switchgear. So R by B again. So this is a current transformer. From the current transformer, this is a three position air switch connection is there. The position of the disconnector can be viewed, and the individual gas compartment can have a separate rupture disc. The separate rupture disc can be or given, because whenever any fault happens, or it is short circuited, or it's a big explosion would be possible. So there are rupture disc given. When the pressure increases more than the design value with a certain margin, the rupture disc operates, and it release the high pressurized gases out. So the this rupture discs are designed to not to have any problem to the user. Suppose nearby any of the user or the persons are nearby, it should not cause the in case of any rupture disc operation, it should not affect the person involved or nearby. That way it is designed to keep it. Now, so we have gone through the three-phase encapsulation and this one already. So when you have three-phase encapsulation, it has less volume of gas, because so normally it is up to 170 kV. People are using three-phase encapsulation. More than 245 kV, people found that it is not economical to go with the three-phase encapsulation. That is a major reason why people are not making three-phase enclosed encapsulation in 420 and higher kV rated GIS. This is a circuit breaker. So when it is coming to the circuit breaker technology, the old technology has been revised, and it has been improving over the years now also. So this is the how it works like, because it is ready to operate. This arcing contact, main contacts, both are in connected condition, and when it operates, this is arcing contact. This comes out, it creates an arc here. Because of the arc, the gas is coming out. It is extinguished in the arc. That's a function of this cell blast circuit breaker. This is the way. This is a nozzle mainly. This is the very important component in the function. So there are various types of materials worked out. Presently, people are using PTFE. Now to improve the performance of this PTFE, people are using the different composition like boron, different materials are tried out to have because erosion is to be reduced, because when the working is taking place, the temperature goes more than 5000 Kelvin. That temperature is easily eroding the surface of the, it changes as the shape, and this angle is very critical. This angle is changed. Because of that, it will lose its properties. For that reason, people are working a lot into to replace this material with a different composition also, and the efficiency of the arc extinction also being improved by coordinating the mechanism with respect to the movement of this. So it's a fully coordinated movement of the breaker moving rod with respect to this profile. That's all people working. So this is just to have idea how the technology has reduced the energy requirement for the magnetic actuator, mechanical drive, spring drive mechanism. So it's buffer mechanism. If you consider this is a one energy unit, and it is over the years 1983, it is about 60%. Now it is reduced about to 20% nowadays. It is reduced to almost 18 to 15% of 1979. You see how much it is improved. This is giving a lot of advantage to the people. So to reduce the noise and reduce the energy to operate the moving electrode. So this is the lever mechanism arrangement at a different position, closing, because there are two springs, a trip spring and closing springs are there. Both springs are coordinated with this arrangement to operate. The energy is stored in the spring, and it is supported by another latch. The latch is supporting, and when it is latch is removed, it operates and it do the function like open, close, and open. It can be used for one more auto reclosion function also, based on the drive arrangement. So other component is a disconnecting air switch. We call it a 3-position disconnecting air switch. Here, these disconnectors are used to both application. So this is conductor. This is the main this one. When it is disconnected, is a disconnector operation. When this is going this side, it is earth position. So this is the disconnector position. This is the earth position. Both position it is operating. So this disconnecting air switch are mainly used in the bus bar and feeder, both side. In circuit breaker feeder side also it is there, and bus bar side also there. So both are used. In certain cases where the bus bar is not necessary to have the earthing switch, people can manufacture the disconnector only without the earth switch here in the bus bar side. So this is that kind of design where you don't need to have the air switch here. But here, most of the all of the base are having the air switch here, and also they also use the high speed air switch because it has a charged energy, charged cable connected systems are connected. That case, it can have a lot of high frequency transient can be possible. That is the reason why we have to have a high speed air switch. This will quickly air the circuit to have a least high frequency noise can be reduced with the usage of high speed air switch. So now this current transformer is inside the gas compartment or outside the compartment. Nowadays, people are using inside. See, the core is always outside the compartment because it is not necessary to have a gaseous gas for the core in the secondary side to operate. So it is used with a small shield arrangement here. This is the insulated arrangement. So the current is not passing through this because this will reduce the function of the current transformer to do the Faraday's. So the people use this kind of spacing to avoid that error measurement error will be very high. That is the reason they have to give this gap. So this can be 3-phase and again single phase. So other than that, the voltage transformer is it's a normal gas insulated is a 3-phase enclosed one, or single phase enclosed also, both are there. Here the current transformer is outside, this design also there. Now people have come up with a new application. This is a LPIT, low power instrument transformer, because these current transformer or voltage transformers are having high power, like in 150 to 200 VA burden requirement for this voltage transformer, and for the current transformer it is in the range of 10 to 30 VA burden requirements. Nowadays, with the advent of new technology of measurement, we have non-conventional instrument transformer or low power instrument transformer. This is governed by IEC 61869-6 and 11. So both are used for this application, where they can use any of the technology available in the market. For example, the olden days people were using the high voltage measurement by resistive divider. The same concept is used most of the medium voltage switchgear, resistive voltage divider, and capacitive voltage divider. Capacitive voltage divider also used in the one of the high voltage and low voltage both application. And optical sensors are used, because optical sensor can be used for current measurement and voltage measurement both application, based on the the crystal through which the light is passed, the fiber optic light is passed. It can be influenced by the Faraday's electromagnetic flux or the electromagnetic field. Based on that, the direction of the light can be tilted. That is calibrated to have accuracy of measurement. Based on that, optical sensors are also used. So application of non-conventional instrument transformer, the installation is very simple arrangement, and signals are free of electromagnetic noise. Measurements are possible over a wide frequency range. Signals can be transmitted over long distance. These are the advantages of the non-conventional instrument transformer. There are specifically, whenever you go with the non-conventional instrument transformer, you have to follow the requirement of IEC 61850 series requirements. So you have to have this is IEC block is primary sensor. As I said, is any of the Pockel sensor or gear sensor or Rogowski sensor, any of the sensor, primary sensors. After that, is a primary sensor is converted. After that, through the cable or any signal line, this is transmitted to the secondary converter or merging unit. There, this merging unit is sharing this to a relay or any other measurement device anywhere. So for the relay operation or anything, it can be given. So this is the general block. The converter can be separately powered. Yeah, olden days, same power was used, but nowadays it can be battery operated. This energy can be given separately. So the consistency, the reliability of the and also noise also very much less, as you are giving the battery operated input. Now, see, this is the example how it is connected. You have a Rogowski coil arrangement and voltage sensor arrangement. Both are arrangement here. You see, this is the box where you have this is a simple bus bar. Over the bus bar, this is kind of this electrical clearance between them, and this is the current voltage sensor. This is a current sensor. Both are given. So this can be used for the application. By using that, you can reduce the space like anything. It means the condenser station almost 400 to 500 mm. Height can be reduced, and at the same time length also can be reduced. You see here LPVT is reduced by this way, and here it is reduced to this much. Current sensor. This is Rogowski coil. Because of the conversion, they have given this. Otherwise, the distance is very less only. And here also one more application here. Here also this is CT. Instead of this CT, they have arranged here the NCIT, non-conventional instrument transformer here, and so space is reduced by applying the replacing the conventional into non-conventional instrument transformer. So here also one of the application in the site, actually they have installed that, and they wanted to observe the difference, how much difference this is giving, and comparing with the non-conventional combined LPIT. This is the box where you have both current sensor and voltage sensor, both are given, and both outputs are compared continuously. But this is not connected with the relay or protection circuit. So only the protection circuit is connected with this. This is only measuring for the comparison in the site to observe the functional requirement of the LPIT. This is the thing. So these are the other components of the GIS. It's insulating spaces. This is a very critical portion because this is supporting the conductor, any conductor from the ground. So if this is not designed or manufactured properly, definitely it will have problem. So this is non-communicating type. This is a communicating type, and it is supporting the conductor. So this is 3-phase. So this we are manufacturing these components in our factory. This is the rupture disc. The rupture disc is in two design. One is it can open and regain its position once it releases it. Another one is that it can permanently it opens. So certain spring operating mechanisms are given here, and it is once the pressure is increased because of some fault conditions, it will open and release the gas, and it can come back to its original position. So here, if you see, this is also the operating persons are here, and the direction of the flow of the rupture disk gas release is this side. You can see this one. So this way it is designed. So surge arrestor, this can be again three-phase enclosed, three-phase enclosed, single phase one. So here this is a surge arrestor. This is a cable connection connected here. This is a transformer connection. The transformer is directly connected to the switchgear. You see, this is a switchgear component. It is directly connected to the. So these are the different connection we have to supply along with this. When it is transformer requirement, there is a adapter given here. So this is a cable socket enclosure. This is a cable. It's for the feeder connection. 3 phase are there. Here cables are connected here like this, and the inside you can see how it look like here. So this is a cable socket. Inside this is a cable connections. You can see very how the connection is, because this will be going inside to make the contact. So this is making contact with the socket or a metal part to continue the flow of current. So here there is a grading and all, it is there. So these are the components of the cable connector. So now we have finished with the components of the this thing, so the GIS. So other than that, the bus ducts also there. I missed it actually. The gas insulated lines are important component. Comparing to the instead of if you see here, this is XLPE cables, or this is a cable. Instead of cable, they can use the gas insulated transmission lines also, or people call it a bus duct. Bus duct can be used. So if you see, this is a GA gas insulated line. This is a overhead line. This is a XLP cable line, 2 per phase. For the 2000 MVA power rating. How much is the losses? If you see that, the important thing, if you can see this AC resistance and the dielectric losses is very less in the line. There is no loss almost, and the resistive losses is also very less compared to overhead lines, because the power transmission also same, and the characteristic impedance is 48.6 compared to this 21 here. Load capacity can be increased based on the temperature, this thing, and the surge impedance is about 48 ohms with respect to 12 ohms here. So these are the advantages of having the gas transmission line. There are some disadvantages, but this can be used anywhere in the underground also, like cables, how it is embedded into the ground. This can be also done. So the energy can be transfer of power can be increased by improving the connections and metallic connections. So these are the electrical characteristics of the GIL at different voltage levels. 110 to 800 kV is shared here, and the capacitance also mentioned. The surge impedance also here given, and the inductance also here. It's up to 2500 amps to 5000 ampere current rating is given. So this also can have a as a pure SFC gas, or 80% nitrogen, 20% SFC gas. Both are there. So here 380 kV and 500 kV GIL gas insulated line, 80% nitrogen. So these two cases, 380 and 500 kV cases, they have used 80% nitrogen, because it is not necessary to have any switching operation there. It is only the electrical insulation requirement. So 20% SFC gas is used by mixed gas technology. So these are the seamless. It's a continuously welded gas insulated transmission lines in the tunnel. So the secondary system has its own measurement, protection, and other units. So this is, we call it a local control cubicle. We can have any measurements, even partial discharge measurement, everything can be embedded into the LCC whenever required, and the HMI, all human machine interface can be made in the LCC. Then the earthing has to have a capacity, because the complete size is reduced into a very small area. So you will have to increase the fault production capacity. So the all mechanical forces has to be taken care, and the current transfer during the fault can be transmitted effectively to the ground. For that, the earthing is very important to have overvoltage protection, potential equilibrium, lightning protection, and these EMC measurements. So these are some of the tests routine earlier done in all GIS, like the electric test, say auxiliary tightness test. This is the gas, how much is there, how much is the leak rate and all. Measurement of resistance of the main circuit, pressure test on enclosure, mechanical operation test. With that, you have all operations, the sequence of operation are done to see the reference values, whether it is matching with the type tested values, and other things, pressure test on partition. These are the routine tests. These are the type test. Type test is not a detailed type test, but it's a list of type tests as per IEC 62271-203. Electric test, measurement of resistance of the main circuit, temperature resist test, short time instant test, verification of degree of protection of the enclosure, this IP protection, tightness test on the enclosure, EMC EMI test, verification of making and breaking. This is very critical test for the breaker and switching elements. Low and high temperature test, proof test for enclosure, pressure test on flat partitions. So normally the enclosures are around 3 to 4 times the rated design pressure is required to be tested for the proof test, and partition also in the range of 4 times the rated pressure is applied to test these partitions, spaces. Test to improve the performance under say these are the cyclic, thermal cyclic recommend. Then the circuit breaker design test, fault making capability, high speed switching operation, mechanical endurance test for the breakers, air switch and disconnector are required, and make proof test for the high speed solve. These are the type test. These are some of the equipments for the measurement of. These are the site assembly details. I think I'll not be able to cover this thing. Additional monitoring of this. Anyway, I'm just giving some of the photographs attached with the related to the different substations. This is substation is in the mobile arrangement. Here also one of the mobile substation in the mixer technology can be directly taken to the AAS, and it can be used for the service. Is now here the transformer is connected directly to the mobile substation. You see. So it has this also has its own standard. The prefabricated substations are there. The standard IEC is there specific to this. So as per that, it has to be manufactured. And this is a container substation ready to use. And this is another arrangement. The completely enclosed this one. This is a cable connector arrangements are coming outside. This is inside the box. See the test as a dielectric test, you can do it in the site. These are some of the tests on site. So I'm not covering the condition monitoring now. I wish to complete it here. Thank you for your patience and listening to me. If you have any question, please you can tell me. Yeah.
Thank you, sir, for your detailed talk on gas insulated switchgear. I would encourage all the participants to post their questions in the chat box or to unmute themselves and ask questions directly. The participants are also encouraged to fill the feedback form available in the chat box. The session was quite detailed, explaining the need of GIS to the technical details involved, displaying a comparative analysis with AIS, cost analysis, and also mentioning alternatives of SF6, the type of enclosures, and finally elaborating on the standards. So if Does any participant posted any question? So if any participants has not posted any question yet, then I would like to ask a question to you, sir. Sir, you said that there are no alternatives of SF6 so far now. So how do you see, like, there is a lot of research going on in finding the alternatives of SF6. So from your expertise, can you comment how far have we reached and how far is left to reach to get an alternative of SF6? Like you said that SF6 is not at all safe for the environment, but it is also one of the best gases for a GIS. So can you comment on that, please?
Various manufacturers like major manufacturer of the GIS have come up with a solution up to 300 kV. As of now, I don't think anybody has come up to the full range, but there are gases available in a lower voltage range and in a higher voltage range still in the trial or experimental stage. There are substations up to 145 commercially available, and it is in even UK. It's a national grid also had tried using the alternate gas. It's particularly G3. G3 was the trade name of GE now. It was a erstwhile Arriva T&D, and they are also using, and others like Siemens and other manufacturers also, ABB, and then it's now Hitachi, are also using different gases. They are coming up with fluoro-free gas because they don't, because some manufacturers have come up with a fluoro-based gas, but the is lesser global warming potential effect. So they wanted to go with without fluorine-based gas. So they have already done some type test up to 145 kV already, and I'm not sure about 245 and above. Is it commercially available? But I think 2012-14 onwards the research is on, and it has not fully replaced up to 420 kV level or more. There are many gases available. I say nitro, the keto, fluorone, fluoryl, nitrile, all many gases are introduced already, and it has its own limitation in terms of liquefaction temperature and arc extinction. Sometimes it is more dielectrically good and is not very good with the arc extinction. So in that aspect, people are still working on that to have a complete solution. Research are still on. There is a paper, I think there's one paper published, alternate gases for the GAS, combining all major manufacturers of GAS also published a paper recently. You can refer that paper also.
Okay, sir. Thank you for that insight. Sir, I have another question is as we know that urbanization has increased a lot. So where do you see GIS as a future? Because GIS will take up quite an amount of space for setup. So like how do you create so much amount of space for a GIS when there is a lot of urbanization already ongoing?
No. This see, compared to AAS, GIS takes very less space. That is the advantage of GIS.
Okay.
So space is limited. Space because if you see the previous slides, it is only 5% of the total volume occupied. The AAS is being used for the GIS. So based on the space limitation, we have to adapt with the GIS application.
Okay.
GIS needs lesser space compared to AAS, because I have shown some of the slides where you have for bay it's about 180-meter length for AAS. This is just 6.5 to 7-meter length only. So it is very less space for GIS.
Okay, sir. Okay. So I think because some of the part of your talk was not covered in this session, we would like to host you again for upcoming webinar soon. So with that note, I would like to end this webinar. Again, thanking you for being our speaker. And in that regard, I would request all the participants to switch on their camera for a group photo in form of a screenshot. Team, let me know when the screenshot is done. Is it done?
Yeah, I have taken.
Okay. So proceeding further, it's our pleasure to have you on board, sir, as a speaker. And in that regard, please accept a virtual token of appreciation on behalf of IEEE DIA Student Branch Chapter IIT Kanpur. And I would like to acknowledge the efforts of entire SBC team and our mentor and faculty advisor for organizing this event. And no event is complete without a lovely audience. So thank you all for being with us. Thank you, sir.
Thank you very much for joining, sir.